All right. Hello, you can hear me well? Thank you all for joining, loud. Thank you all for joining us as Northwestern's homecoming weekend is getting started. I hope those of you who are here for the weekend have a great time. And thank you for choosing to be here tonight. My name is Vicky Calogera. I am the CIERA director and also a professor in the Department of Physics and Astronomy here at Northwestern. It is so exciting to see so many of you here. This has turned out to be a very big event for a very good reason, given the speaker we have. Tonight's annual lecture is a long-standing event and series that we've been organizing for many years, thanks to awesome staff and numerous volunteers that I would like to thank, because without them, none of this would be organized as well as it's running behind the scenes. So I'm really proud to host all of you every fall, and I'd like to give a thanks to many of our volunteers. There's many more behind the scenes that you can't see even tonight. I would like especially to thank our steadfast supporters and sponsors of this event and series, the Alumnae of Northwestern, and as well as CIERA's Board of Visitors, members of which are here in the audience. Thank you for being here as well. Now, CIERA, some of you know that CIERA is closing up on a whole year of celebrating CIERA at 15. Next year, we'll be celebrating Sweet 16. Who knows what we're going to do then. And I'd like to draw your attention to a new webpage that we have established, spearheaded by a Medill undergraduate intern at CIERA, who discovered and put together through interviews a story about the rich history of astronomy at Northwestern that actually goes back to 1887. So please make sure to check it out when you have a moment, and you can see the QR code up there. But as you know, CIERA is more than just astronomy. Our exploration, our people, and our impact reach well beyond astronomy to many other disciplines in science and engineering, and in also arts and social sciences and education. I hope you got a flavor of this from the slides that were rotating earlier, and throughout the events that we organize through the year, but also programs we have for students in the summer and also throughout the year as well. Before you leave, I'd like to ask you on your way out to please take a moment and fill in our survey. You'll find QR codes on boards, I believe, outside. And if you fill in the survey correctly, which means if you provide your contact information, then you'll be in a raffle to receive a CIERA t-shirt, which is gorgeous, isn't it? At the end of the lecture, tonight, the Rubin Observatory will be open for observing. So you're welcome to make your way on your own to the Rubin Observatory, or look for volunteers who will be holding flags and form groups and follow them as they take you to the observatory, if you are willing to continue your evening in that spectacular way. Now, it's a real privilege for me to be in a position to introduce someone who has transformed and shaped the fields of physics and astronomy in profound ways. Professor Christopher Stubbs from Harvard University is an experimental physicist who works at the boundary between particle physics, cosmology, and gravitation. He has been at Harvard for over 20 years, and he has served as both the physics department chair and also dean of sciences, most recently, actually. Among many endeavors, he was a pioneer for the searches of dark matter, and also he was a member of one of the famous teams that discovered the accelerating universe. Most relevant to the talk tonight, he has been deeply engaged with the Rubin Observatory all the way from its beginning. That goes back to 30 years. He was the inaugural project scientist, but also he's deeply involved in the engineering of the telescope. And in fact, the past year, he spent it all in Chile as the telescope and the project was coming up to first light, taking the first observational data. And he was heavily involved, as I said, with the last few stages of engineering steps. For his work, he has been honored with many, many awards. I will mention just a few of them: the NASA Achievement Medal, the Gruber Cosmology Prize, and the Breakthrough Prize in Fundamental Physics. Now, his most important achievement, though, he says, is the fact that in 1975, he was fly fishing champion in Iran. Now, he's fishing for the secrets of the universe. Help me welcome Christopher Stubbs.
Oops. Thank you. Thank you, Professor Calagera. Well, thanks for being here. Thanks for your interest in astronomy. I'm going to tell you about a really exciting project that I think is going to transform our field, and I hope you leave here with the sense of why we think that's true. So this photograph is of an observatory that is just in the process of being born. And what I'll do is go through an introduction of what this observatory is, why we named it the way we did, go through the enabling technologies that have propelled our field and how they all came together in this one particular system, tell you a bit about what the science objectives are, which span a wide range, everything from the solar system to the universe at large, talk about what it's going to do in the coming 10 years of operation, spend a little bit of time talking about the sort of astrosociology of doing really large, approximately billion-dollar projects, and how that presents both opportunities and challenges in our field. And then a little bit of time at the end about a new disruptive technology that I think is changing a lot of science and engineering, and that's artificial intelligence, and how that's going to change the way we do our business. And then plenty of time at the end to take whatever questions you might have. Sound good? Okay. So the goal of this observatory is to take sequential images of the entire southern sky, sweeping back and forth, and take a 10-year-long time-lapse image to unprecedented depths and find really faint objects. That's its goal. It's named after Vera Rubin, I think entirely appropriately. Vera Rubin was one of the pioneers in our field who in the 1970s really showed the physics community how little we understand about the universe that we inhabit. So Vera Rubin measured in galaxies like the spiral galaxy here, how fast the outer parts are rotating as a function of distance away from the center. And if all you do is add up the mass of all the stars and make a prediction of what this rotation profile ought to look like, it's the dashed line. That's not what the data show. The data show as you move further out, this rotation curve just gets flat and keeps on going. And the conclusion from that is that galaxies like our own Milky Way are predominantly made, 90%, made of some mysterious stuff we call dark matter, the nature of which we absolutely do not understand. And so because a big part of the science mission of the Rubin telescope is to go work on this dark sector of the physical sciences, I think it's really entirely appropriate to name the telescope after her. She was one of the heroes in our field. That dark matter scenario is part of the overall understanding that we have about the origin, composition, and fate of the universe, and that's shown in this picture here. So here we go. Are you ready? The universe started 13.8 billion years ago in some big bang that was actually, we don't know why that happened. We have no idea. But it was at such an energy scale that quantum mechanics played a really big role. So quantum mechanical fluctuations bouncing up and down created variations in the initial conditions of the universe that the dark matter rolled into. And at the same time, the universe was expanding and cooling. In the first few moments of the universe's existence, it expanded by some huge factor. It got blown apart in some early era of cosmic acceleration we call inflation. And when that happened, the universe cooled, and it cooled and it cooled and it cooled until the nuclei and electrons that were there cooled enough that they combined to form neutral atoms. As soon as that happened, the universe became transparent to light. Prior to that, it was just this plasma of dark matter, photons, ordinary electrons and protons, and we can see the imprint of those density fluctuations in the light from the early universe in the cosmic microwave background. So you can actually go out and make measurements of this baby picture of the universe, and these hot and cold spots that you see are variations in the strength of the gravitational field where the dark matter puddled, and then over time, the gas fell into those density fluctuations and started to form stars and galaxies. So the James Webb Space Telescope that you've probably heard about is actually probing this era of the early origin of structure. But that was all promoted by the dark matter that Vera Rubin showed us existed. Things coasted along, stars were formed, explosions happened, recycling of material in stars and galaxies, and things went happily along until roughly halfway through the age of the universe. As it was expanding, the density of all this dark matter and the ordinary contents would fall, because we started with a certain amount of material, and as the universe expanded, that became less and less and less and less dense. And as the universe expanded, we made more and more and more space between galaxies. And what we discovered, to our shock, horror, and surprise, when people were expecting to make measurements of how much is this expansion slowing down because of the gravitational attraction of the contents of the universe, it was an astonishing observational discovery to find this rate of expansion is not slowing down at all, it's speeding up. The expansion is going faster and faster and faster and faster, and actually expanding exponentially, such that in the very distant future, any galaxy that's not gravitationally bound to the Milky Way will become unobservably far from us. And so there's a tension here between the dark matter and the gravitational attraction of the dark matter promoting the growth of structure, and this, what we call dark energy, which is sort of, believe it or not, repulsive gravity between adjacent pieces of vacuum, seriously, blowing things apart. And what's really interesting is we have two predominant theories of physics. One is general relativity, and one is quantum mechanics, and we don't know how to plug those two together. And if you go in every physics building that I've been in, the theoreticians are on the top floor, okay? Because they're like special. So you get your oxygen tank and you start climbing the staircase to go to where the theoreticians are, and you get up there and you say, hey, do me a favor, you tell me the world has this quantum mechanical energy in the vacuum. In ordinary classical physics, it's easy to describe what the vacuum is. Just take out all the billiard balls and pulleys and Newtonian stuff, and if you've taken everything out and there's nothing left, that's the vacuum. But quantum mechanically, the vacuum is really complicated. It's this seething turmoil of particles and antiparticles being created and annihilated, and it's really foamy and it's really energetic. And if you say, do me a favor, compute the cosmological consequence of all that energy content in the vacuum. How big is it? And give it to me in units that I can understand, in like cosmological units, none of this h bar c equals 1 stuff. So they go away and they go on the blackboard, and they come back and they say, well, we sort of have a problem here, because actually in the natural units of astronomy, this energy content of the vacuum is 10 to the 120th, okay? Which is the most wrong prediction in all of science by 120 orders of magnitude, okay? But they're not silly people. They say, but no, wait, actually, we know that can't be right, because if that were the energy content of the quantum mechanical vacuum, the universe would have never done this. We would never have made structure. It would just blow itself apart. Therefore, they conclude that can't be correct. And we're like, yeah, that can't be correct. And so they say, well, the only natural thing that can happen then is there is an exact and perfect cancellation to 120 significant figures that makes it exactly 0. And with absolute confidence, we hereby tell you that it's identically 0. And we say, well, thank you very much. And then we went and measured it, and it's 0.7. Okay? So you don't have to be a mathematician to know that 0.7 is neither 0, nor is it 10 to the 120th. It's like randomly in between. And that is actually one of the biggest puzzles in all of contemporary physics. Why on earth, when the two natural values, one of which is clearly excluded by the universe that we inhabit, it didn't have the value 0 that they wanted? Why is the dark energy the way that it is? We have no idea. We are living through an intellectual revolution every bit as profound as when quantum mechanics was discovered. We're just in the really confused part of it, okay? And we're in a profound state of confusion, believe you me. So that's the overall story, and this is part of the science case for the Rubin telescope. So that's why in the bottom left-hand corner, a big part of the science case is the dark sector, dark matter and dark energy. And this telescope was engineered to go after those problems. But along the way, with the same data set, we can probe the structure of the Milky Way. We can do a census of the solar system and look for potentially hazardous asteroids. And by doing this time-lapse imaging of the entire sky night after night after night after night, we can open up the time domain of astronomy. Okay? Are we good? Onward? Okay. So I thought I'd take you just on a little trip of what it's like to go there, because it's way cool. So the Rubin Observatory is situated in Chile. Most ground-based, cutting-edge astronomical observatories, including the Giant Magellan Telescope, are situated in Chile because the observing conditions are better than anywhere else on the planet. And here's a picture of the telescope dome up on the ridge in Chile. So here's the deal. If you start in Boston, you fly, boom, to Houston, and then, boom, to the capital of Chile, Santiago. You get on a domestic airplane and retrace your steps and go a little bit north, 1 hour flight north, to the seaside town of La Serena. Here's a picture of the town of La Serena. It's a gorgeous place, really good seafood restaurants. But we're not so much interested in being in La Serena. If you want to go to the telescope, it's a 2-hour drive. So you drive inland and you go south and you go up this valley, which is the Elqui Valley, which is in Chile, kind of a combination of the Napa Valley and Roswell sort of merged together. There's like this whole alien thing, and they grow a lot of grapes, and it's really interesting. So you go up the Ruta de las Estrellas, and this Blackwater Pass, 100 some odd miles east, is actually the border with Argentina. So if you keep going, you go up over the backbone of the Andes at 14,000 feet and back down the other side. So if you go along this road, here are all these grapes that are being grown. They make pisco, the national drink of either Chile or Peru, depending on who you believe. And as you go along, you drive up in a minibus from the town and the office building in town, and this tunnel up near the reservoir was actually made wide enough to take 8.5-meter telescope mirrors through the tunnel. It was enlarged in order to accommodate, and that gives you a sense of the size of the collecting mirror of the Rubin telescope. So you drive along, and eventually you reach a gate of the compound of the land that the US astronomers have bought to keep bright lights away from the observatories. This guy checks with the guy at the gate whether your name is on the clipboard, and then they get given this box that they plug into the cigarette lighter, and the claim is that this contains a GPS receiver that tracks how fast the bus driver goes up the road to make sure they don't speed. I'm partially convinced it's actually completely empty, and it's like a placebo thing, but it does keep people from driving too fast. So you drive on along the road, you drive about 45 minutes, and then finally you come around a corner, and up on the ridge above your head is a 10-story high telescope enclosure, okay? And you stop off at a little canteen, you get yourself breakfast that's avocados and bad coffee and stuff like that. And you go up and enter the telescope dome, and you know that you're there at an altitude of 9,000 feet because your Dorito bag self-inflates to a significant pressure. And you get greeted by smiling colleagues. This is Ilana Urbach, a research scientist in our group. Laram Segev is an undergraduate who spent some time there. And if from turning that way, you turn around and look at the control room, here's the control room. So lots and lots of computer screens. Here's Stuart Marshall, here's Pierre Antilogus. So it's a really fascinating place, and it's just a wonderful part of the world. Incredible wildlife. It's on the edge of the Atacama Desert. And if we had not taken the turn off to go to the observatory, had we continued up the road towards Argentina, this is what the terrain looks like. Okay? There are stone trails along the side that are pre-Inca, that are footpaths that go across the backbone of the Andes. And these waters actually hold trout, caught trout up there. So, but let's go back to the telescope, and end of travelogue here. So the three big enabling technologies for this project are a combination of making really large precision optics, which for some reason they let my colleagues sit upon. I still don't understand why that happened. The availability of really large silicon detectors, CCDs, and cutting-edge high-volume data processing, which is a little hard to represent in an image, so pardon the picture. And all those three come together and make this telescope possible. So to give you a sense of how this works, the main mirror has two pieces to it. It's 27 feet across, and light comes down and does three bounces. It hits the main mirror, bounces back up to the secondary mirror, which is itself 5 meters across, hits this fishbowl tertiary mirror, and goes through lenses into the camera. And these things are rotating filters that move into position over the camera. So that's the optical path through the telescope. And the camera itself has a lens in front of it that's 5 feet in the diameter. It's the largest transmissive optic ever made, to give you a sense of scale. So this telescope will scan the entire sky. The number of pixels in the camera is 3,200 megapixels. It takes 30-second exposures. It'll scan the entire night sky sequentially. Every night we generate 20 terabytes of data. And in terms of finding things that move or change on the sky, 10 million alerts per night will be generated of things that are new and different. So the data flow down optical fibers to a computer center in the US and in Europe. And within 60 seconds, these images get sent. We analyze them, and within 60 seconds find everything that changes or moves, classify it as an asteroid, a supernova, a variable star, some strange new thing. But there are less interesting things like cosmic rays and satellite and aircraft streaks, so we distinguish all those from each other and then send this fire hose of information to places like this university that has a strong presence in time domain astronomy, and then they get to choose which of those they're going to follow up and pursue. Taking a large sequence of images on the sky lets you do two things. You can add and you can subtract. So if you take all the images and add them all up, just collapse them all together, it's as if you took one super long exposure of the sky, right? We can go really deep if we add them up this way. Going the other way, if I subtract the image taken tonight from the image taken on a previous night, I can find everything that changes or moves in the entire static sky is suppressed. So we execute both of those data analysis paths. And just here's a bunch of bragging numbers. At the end of the day, 15 petabytes of data, annual data releases, 20 billion galaxies, 17 billion stars. So I think that's all okay, but let me convey to you how different this is, because I don't think those numbers convey it. So I'm going to show you a sequence of images of how the technology has evolved, starting from the 1990s, when on 1.5 meter class telescopes in both hemispheres, people used photographic plates that were about this big, that had photographic emulsions that were not particularly sensitive, and they did a couple of sequences of passing on the sky. So this shows you little fuzzy images of galaxies. Here's a hot star, here's a cool star, and that's kind of like the state of the art in the 1990s. When you move to detectors that are silicon detectors, the Sloan Digital Sky Survey in the 2000s gives you a little better spatial resolution. You start to see colors a little bit better. Things are progressing forward. If we then go to the next generation of surveys, the Pan-STAR survey, done in Hawaii, it took longer images. It went about 6 times fainter than the original Palomar survey. If I take the images that we took from our telescope in the fall of last year and take 1,000 of them and stack them all together, here's what you see. I think that conveys why this is a different system. Okay? Yeah, you want to see that again? Ready? Like that. Okay? But watch this. I'm going to go back and forth a few times. Okay? Do you see this guy over here? Watch this one. Ready? Boom, boom, boom. Is it moving? Is it an asteroid? No, asteroids go way faster. It's actually a star in orbit around the Milky Way whose motion is enough that over that time period you actually detect its motion. And so that gives you the sense that the sky is not static. Even though you're used to all these pictures in astronomy textbooks that make it look like just nothing going on, that's not true. So we can take the data that we have and do the find things that change or move trick. And so here's a picture of what we did in the first week to find asteroids. We see stars, we see galaxies, and we see things that move. And the things that move that fast are asteroids, and boy, did we see a lot of asteroids. Okay? So I'm going to show you new discoveries of asteroids that were not known. In the first night, 1,000, oops, sorry, wait. I screwed it up, hang on, let's go again. Oop, wait, we'll go back to here. Hang on, bear with me. I'm going to have to play it again. So in the first night, 1,000 asteroids, I'll let it go for a whole week, and you can see how it all piled up, okay? Sorry about that. So 1,000 in night 1, 1,300 in by night 2, 1,400 by night 3. By the end of the first week, 2,000 brand new discoveries of main belt asteroids in the region between Mars and Jupiter in the solar system, and a few things way further out here also. That's the slice of the main asteroid belt that we looked at in the first week. 2,000 brand new things. And there is some likelihood that there's some asteroid out there that has our zip code on it, right? And those potentially hazardous asteroids are worth finding because if we can find them early enough, there's a chance that we could do something about it. So part of the telescope's mission is to do a search for potentially hazardous asteroids. But that's only part of the science case. There's this other broader sort of lots of things on the sky change. And so let's look at that aspect of things. We can take images where we get rid of all the asteroids and go deeper. And here you can see star-forming spiral galaxies, red elliptical galaxies whose star formation is finished, gravitationally bound groups of galaxies called galaxy clusters, all these things of different colors or stars of different temperature, giant ellipticals at the center of other groups of galaxies. And then my favorite piece here, you can zoom into a cluster of galaxies. All these are gravitationally bound together. I'm guessing at a redshift of 0.3 or 0.4. And it just gives you a sense of the sort of depth of our ability to do this, because at some level, if your scientific interest, oh yeah, one other point, that whole part of the sky is a couple of fields of view wide, right? So that's 2 images going really deep. We'll get 1,000 times that much by the time we've covered the whole southern sky. So it'll be just this unprecedented map of what's going on down there. And from the standpoint of people whose interest is outside the solar system, all those asteroids are like, get it out of my face problems, but we can easily excise them from the data and send the data down multiple tracks. And so in the history of astronomy, we've had surveys like this before, but a lot of the use of telescopes has been, you put in some application, James Webb Telescope works this way, you put in some application, they decide your project is meritorious, and they point at your favorite thing, and then you get the data. The multiplicative science gain here, of being able to do all those science cases at the same time in parallel, is truly unprecedented. So it's sort of a step towards democratization of science and empowering a lot of things to happen at once. Among the things that change on the sky are exploding stars called type 1a supernovae. This is what we used in the original discovery of the accelerating expansion of the universe. And this graph shows this going vertically up is things getting fainter, and moving out in this direction to the right is the redshift, which is the amount by which the light stretched as it was traveling across the universe. So the redshift is really a measure of the cumulative history of cosmic expansion. And so if we know how far away these are, and if these things all have the same amount of light emitted every single time, then we can infer how long the light has been traveling. This tells us by how much the universe has expanded. So type 1a supernovae are a direct, model-independent measurement of the history of cosmic expansion. And if the universe were not accelerating, the data would land on this dashed blue line. And I'll leave it to you statisticians in the audience to decide whether the data are consistent with the dashed blue line. I don't think so. Okay, so much for all those theoreticians. So let me show you what this telescope will do for type 1a supernovae. So our entire telescope was engineered to go after this dark sector pieces of the pie that completely dominate the universe that we inhabit. Not only is Harvard not at the center of the universe, but it turns out that actually we're not even made out of the same stuff that most of the universe is made out of, which is this little tiny, everything in the periodic table, all the science that happens in the building here, all the chemistry, all the biology, everything that's not astronomy or fundamental physics is this little tiny blue edge right here, okay? So the telescope was really engineered to go after this dark sector piece. And here's a plot where this is a logarithmic vertical axis, so every step is a factor of 10. Currently, we have around 2,000 type 1a supernovae that we can use for cosmology. By the time we're done with this Rubin project, it'll be 500,000, okay? Just to give you a sense of just how different that is. But if we're gonna reap the benefit of that many objects, we need to do a much better job on the precision of the measurements that we make. So another place where this project is gonna break new ground is the precision frontier of astronomy. And one piece of that is to measure in exquisite resolution what the sensitivity of the telescope is to light at different wavelengths. And so we built a system with a tunable laser that lets you actually go through wavelengths and broadcast into the telescope a calibrated amount of light at each individual wavelength, and we just go doop, 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 step through wavelengths and measure the throughput function of the telescope in a way that's completely independent of any celestial flux standards. The project is going to take data in 6 different passbands. So this is wavelength going from the ultraviolet out to long wavelengths that you can't see, and it breaks it up into different filters that sit in front of the beam, and we get these multi-filter images sequentially on the sky. And that's all great, except it turns out we're on the ground, and when you look up through the Earth's atmosphere has a transmission function that looks like this. It's kind of a mess. And in fact, parts of it are actually variable. There's water vapor that's variable. There's attenuation from atmospheric aerosols. The ozone content in the atmosphere changes. So if we want to be super precise, we need to be able to measure and compensate for all these variations in atmospheric transmission. And so this is a bit of a surprise to me. Professor Caligari mentioned I was the inaugural project scientist 30-odd years ago. I said, damn it, we should have a telescope whose only job is to measure the transmission of the atmosphere. And lo and behold, there it is. See him right there? Okay? It actually survived all the project reviews. I got away with this. I think it's great, right? So that telescope's job is actually to measure the transmission, and then in the data processing, we fold it into the images that we get from this. So this is the main telescope dome. From bottom to top, it's 10 stories high. And to give you a sense of scale, we'll fly around in a drone, and you can see cars over here. You'll see on the bottom right here a couple of people, and that gives you a sense of scale of the enclosure of the observatory. So where are we at? you can tell by now, these little these dots over here on the left go like a long way over to the left, right? It's been 30 years to make this thing happen, of cheerleading, fundraising, engineering. But okay, so it got built. And towards the end of last calendar year, we got the first images on the sky. And that was sort of our teething. And that was a successful undertaking. We then installed the main camera. And in the spring of this year, released the first look images from the main observations. We're now in this sort of commissioning and verification period with the expectation of going into full survey operations in late calendar 2025. It was a rather jubilant moment when the dang thing worked. And I think we're past the point of some blank moment where we see some horrific thing that was not built right or not engineered right or whatever. I'm, at this point, even as a pessimistic person, guardedly optimistic that this thing is actually going to work really well, okay? You do know what a pessimist is? It's an optimist in possession of the facts, okay? So things are actually doing pretty well. The good things are the telescope and the camera work, the software works really, really well. It gets as many photons through it as we expected. We have attained sharp images on the sky, which is a really important thing for doing astronomy. That's all great. Full disclosure, a couple of surprises along the way. There are weird things in the detectors. The point spread function depends on the flux of objects. Pixels have rubber sheet elasticity. There's phosphorescence. We'll figure that out. It's actually hard to appropriately baffle the undesired light through these systems. And so we saw really cute things like this, which we called angel wings, out on the edge of the detector. And it took actually about a week to figure out why this was happening, what was causing it, and what we'd have to do to fix it. So this is just like bread and butter experimental science. You iteratively identify and solve problems, but there's no showstopper problem here. I hadn't really appreciated until we got to this point that I had this unappreciated deep fear in my heart, which is that we would build this thing and nobody would care. Okay, that it was like, field of dreams, people would shrug, they'd walk away like, oh, that's someone else's science. That has not turned out to be a problem. And even in the few weeks since these initial data were released, boom, 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 a succession of science papers have come out where people have just pounced on this and done actually all manner of really creative and cool things. So that's been pretty awesome, including citizen participatory science. So I would just draw to your attention that there's an opportunity for everybody in this room to look at and inspect Rubin images and identify instances when we have found comets on the sky, all right? And the project's philosophy about data release is that there's no proprietary data period. The data flow right out to everybody, K through 12, all universities within the nation, and all data entitled institutions. So I just think this ability to harness it, to capture the imagination of young people and have them be full participants is just absolutely awesome. I did my PhD in a small tabletop experimental physics research group. The number of co-authors on my main PhD dissertation paper was 8 people. The number of co-authors on the paper for the discovery of dark energy from our group was 20 people. Here's how many people came to the 2024 community workshop for the Rubin telescope that were scientifically interested. And if you want to play Find Waldo, it's like, that's me right there, okay? So this is a huge sociological shift that most of us don't get trained for operating in these really big teams. And both in my role as a sort of mentor and engineer and project scientist, you have to talk to all these project manager people who talk about risk mitigation and work breakdown structure and earned value management and budget overruns. And you have to learn how to talk their vocabulary. And nobody ever bothered to teach that to me. So I learned all that sort of on the job, and I decided that I'd write it all down. So I actually tried to write a book about what it means to make this transition into big science, because actually it's an increasing part of what's happening in all fields, in biology, even in the social sciences. And so in return for not getting any royalties. MIT Press has made it freely publicly available, so if you want to get a PDF version for freebies, you can snap the QR code. If you want to pay Amazon money, you can get a hard copy, but it's not worth it. Thinking about artificial intelligence that just sort of happened in the midst of this project and what impact does it have, that's also been really interesting. So, you know, ChatGPT, all this really cool stuff, you just tell it what kind of computer program you want, and there it is. That's all really cool. So when ChatGPT broke open, I actually went to the software managers on the Rubin project and I said, there's this really cool disruptive technology that's going to change everything that we do. You have 50 people on your payroll. Can you break 2 of them loose to come work with us on the artificial intelligence side of things? And the project managers, being very well-disciplined project managers, said, oh, you don't understand. We have deliverables. We have a schedule. We have a budget. Everyone's allocated to existing tasks. No, we're not going to break anyone free. And so in response, the scientists on the project started some little kind of insurrectionist demonstration projects to show that this stuff is going to work. So I think ways in which artificial intelligence can impact what we do are the scheduler and avoiding clouds. I'll say a bit about how we collimate the optics using this, optimization of the airflow, listening to everything in the telescope and deciding when it's on the verge of failure. I'll show you examples of English language data browsing and extracting information. We have 25 years worth of documentation that nobody can get to understand or read, and that's a great application for large language models and troubleshooting. And for the data processing side, the astronomical community, and I want to highlight a lot of great work being done here in this broad domain about how do we go from information as pixels on the sky to database representations of attributes of objects. And a lot of that can be propelled by machine learning. So I'll tell you about just a handful of these to give you a sense. Using data from current generation surveys, people have done a really good job. So here's like before, after difference. So there's a, you know, some variable thing in the center there. This thing looks like it might be a supernova off on the side. So they go through and categorize these things into, is it an asteroid, a supernova, a variable star, using machine learning methodology. And that's been really quite successful. One fun thing that we did on the summit this last fall was to build artificial intelligence into analysis tools so that you could just in English say, please make me a histogram of mount image degradation for all images with exposure times longer than 5 seconds, carriage return, and boom, here's the histogram. So could we have written code to do that? Answer, yes. It would have just taken 50 times longer. So, you know, one thing that I've heard said is the most contemporary current programming language is actually English. But it's going to be even more radical than that. There are papers coming out that are basically saying we can use artificial intelligence expert systems to generate entire data processing pipelines that do every bit as well as what the domain scientists wrote. So from that paper, we developed a method that combines code mutation system with the ability to integrate complex research ideas. The ideas could come from lots of different places. The system creates code that can follow a specific idea. It can search over externally supplied ideas. We demonstrate over a wide range of scientific tasks that reaches an expert level when integrating and exploring complex research ideas. This is going to completely change the way we do our business. And it's a really exciting time. I don't think any of us know how this is actually going to turn out. So let me just sort of wrap up here and say, this has been a big team undertaking, literally hundreds of people, decades. I want to thank everyone in the room because your tax dollars funneled through federal agencies made this happen. But I think you should be proud of that investment. I think it's going to turn out to be just a truly extraordinary thing. So if you're interested in learning more about the observatory, here's the link to the Rubin Observatory webpage. If you're interested in learning more about comet catchers over on the right-hand side, if you care to participate, there's an opportunity to do that there. I'll leave that up for a second for people who want to capture it. Tell me it worked. Did it work? Okay, cool. And With that, happy to take whatever questions you might have. Thanks for your attention.
Hello, Dr. Margaret Johnston from the University of Nevada, Las Vegas. One of the questions that I had is that you mentioned that you have this nice little auxiliary telescope that looks just at the transmission through the atmosphere in order to correct the observations that you do. How much of a problem are the communications constellation satellites going to be?
Yeah, great question. So let me just repeat in case people didn't hear. Companies are putting thousands to tens of thousands to, over this decade, perhaps 100,000 satellites in low Earth orbit. And it's certainly true that when those are illuminated by the sun, they streak across the sky and are bright enough that you can see them by eye, let alone see them with our telescope. They're there in great abundance. It's a problem, but it's not a devastating problem for us for a couple of reasons. One is, for most of the night, the part above the Earth where they are is in the shadow of the Earth. So they're actually not illuminated by the sun for most of the night. The times that are problematic are in twilight over near the horizon. Now that just turns out to be exactly the place where you want to observe to detect a near-Earth asteroid. Okay, so it impacts most heavily the search for near-Earth asteroids, but the satellite streaks are quite distinctive in the images. It's not like you're going to mistake it for anything else. And so worst case, you just veto all those pixels, and the fraction of pixels that we have to veto to do that, even with 100,000 satellites, is not a huge impact. I'd say it's an inefficiency and an inconvenience, but not debilitating.
So you mentioned earlier the James Webb Telescope, and like I'm trying to understand the difference in functionality between a telescope that's on Earth, that's on the surface of the Earth like this one, and like one that's launched into space, both into like what they're capable of and what they're being used for. Yeah.
So great question. So to summarize that, how come the heck we built it on Earth and not in orbit? Is that your question? So my answer is astronomy is basically a discovery-based observational science. And the diversity of tools that we put into operation across a wide range of wavelengths doing a diversity of science projects is an imperative for our field. And ground-based telescopes and space-based telescopes are in many ways complementary. We would not have been able to launch this into orbit because there is no rocket big enough to accommodate the primary mirror. James Webb Space Telescope unfolded post-launch to get a large aperture. The big benefits of putting things in space are A, you're above the Earth's atmosphere, duh. And so that means that the images can be sharper, you don't suffer the atmospheric attenuation, but really importantly, it turns out trying to do infrared astronomy, which we're not doing, trying to do infrared astronomy from the ground is like trying to observe in the dome when it's on fire and the lights are on. Just there's so much infrared background, but if you go into space, the infrared background is a factor of 1,000 lower. So that's why James Webb Space Telescope is such a powerful thing in space, is because the infrared background is so much lower. So I think it's really this combination and diversity, and all current space telescopes have a minuscule field of view compared to Rubin. So I'd say they're largely complementary. It's a great question.
One right there. Okay, then let's wait. We'll take the larger name. Let's take one here.
So what happens if the AI fails? So like, because you can't check it with another AI if it bugs.
Next question. So I think you're absolutely right, and it is absolutely without a doubt something to worry about. I think These tools are new, they're imperfect, and they deliver things to us that are not always true. On the other hand, I would ask you how much of the information that you currently consume is assured to be true. So it highlights and accentuates an already existing problem, and at least for the things that we intend to use it for, there are checks and balances in place. It's not going to move the optics to a place that they shouldn't go, right? There are hardware and software limits. I do think a sort of extension of your question is, so let's just find out, how many people actually use things like ChatGPT and its kin, right? So lots of hands go up, right? If you ask it the same question twice in a row, do you get the same answer? No. What's the fundamental assumption in the scientific method? If you do something twice, you get the same answer, right? So as these tools progress in their capability and move further upstream in the scientific method to where they're doing some of the science, I think there's actually an almost philosophical collision ahead of us where the lack of repeatability and lack of replicability of these tools is going to collide with our expectations as a scientific method. I'm worried about that version of your question.
On the other side now?
Hi. You have a beautiful telescope. I'm wondering, do dark matter scientists already have an idea of like some big killer things they want to see once data starts flowing for confirming or denying dark matter candidates? Or is it more like observing something that's unexpected and then working from there?
Yes. So I think, yeah, so let me give you an idea of what this can do for dark matter. So one of the really cool techniques in astronomy is called gravitational lensing. If you have objects that sit behind other objects, the gravitational field of the things in the foreground distort what you see in the background. And we can use the colors of galaxies to estimate how far away they are. And we can essentially do a reconstruction of the three-dimensional matter density in the universe out to redshift of about 2. And that means we can basically watch the collapse and formation of galaxies and mass on the sky into the tendrils and sheets and filaments that characterize the large-scale structure. And that growth of structure is driven by the properties of dark matter. And so by looking at the evolution of large-scale structure, you can actually constrain the physical properties of dark matter. Now, is that going to tell you what it is? Not directly. I think we probably need, laboratory physics experiments to do that, but I think it can certainly tell you what it isn't. And that's actually a good way to make progress in science. The other thing we can do is extend, you remember that little star that went ding, 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 that was moving in the Milky Way? We'll detect the orbits of lots of stars in the outer regions of our own galaxy. And those motions, just like Vera Rubin did, can be used to constrain the dark matter distribution in our own Milky Way, I think, to much better precision than we've done before. So I think we have those like sort of indirect ways to look at its properties.
Any questions here? I see a hand with this one. Let's see your hands when you're done. Let's come to the front next time.
Hello, thank you again. My question was, why in particular did you use a CCD for this type of telescope as opposed to a different camera sensor? And like, what are the sort of challenges of making the camera as big as the Vera Rubin Observatory?
Yeah, great question. So the detector technology that we use was driven by the desire to get high sensitivity and high resolution. So for the experts in the audience, how come we didn't use CMOS sensors?
Yeah.
And the answer is because 10 years ago, when we had to make the technology down select, there weren't scientific CMOS sensors. But separately, actually, our sensors are kind of special in that they are 100 microns thick. The pixels are 10 microns on a side. So our pixels are like skyscrapers. They're 10 times taller than they are wide. And the reason that the silicon is so thick is that gives us greatly increased sensitivity at near-infrared wavelengths around 900 nanometers, which CMOS sensors simply don't have. So I would say there was a factor of 10 gain in quantum efficiency by going with CCDs.
Thank you very much.
This is fun.
Do you think the Rubin Observatory will help us to discover Planet 9 if it exists?
Yeah, so Planet 9 is, do you know we used to have 9 planets? So don't even get me started on that one. There's a hypothesis that there are other planets in our solar system. We'll certainly get, as you saw, a big census of things that are orbiting in the solar system. The definition of a planet is clearly a little bit time variable. There are certainly scientific papers that talk about the detectability of a hypothesized, far away, highly massive planet. And I can't remember the numbers off the top of my head, so I'm not going to make it up, but my recollection is that it would be difficult for that hypothesis to evade detection in the Rubin data set. But I'm like 80% confident of that answer.
Okay, let's take maybe another one here. Oh, okay. All right. Yes?
I know you might have said this before, but is there a factor or exponent in which the universe is growing?
Yeah, so let's see. The answer is yes. And what's the easiest way to say this? If we're right about the properties of dark energy, up until now, the expansion has been kind of linear in the sense that move the clock forward by a factor of 2 and the universe is about twice as big, right? If this dark energy idea is correct, then the growth is not linear, it's exponential. It goes like e to the time, which means it doesn't go like this, it goes whoop, right? So not only does it expand, but it expands faster and faster and faster and faster. And the reason for that is because as it expands, you grow more vacuum. What's that vacuum doing? Exerting a repulsive interaction on the vacuum next to it. So that makes more vacuum. Oh my gosh, we got more repulsion, and it just kind of runs away. Right? So I think my answer to your question is it's an exponential process. And that's a big deal in science, right? Things that are exponential run away pretty quickly. And we will eventually collide with the Andromeda galaxy and merge into one galaxy. But everything that's not gravitationally bound to us in Andromeda is going to move so far away that you can't see it anymore. Have a nice day.
Hello. Is the telescope upgradable? And any plans for upgrade besides software?
Yeah, so that's a great question. You saw the time scale to get this thing built. If the survey that we're about to embark on is 10 years, it's already late to be answering that question. So we have had a bunch of workshops about what might we do. And it ranges from replacing everything on the focal plane with infrared sensitive detectors. But because of what I said before, that's not a great thing to do on the ground. We're better off doing that in space. And NASA's about to fly a big infrared space telescope. That doesn't sound like a great idea. We could make it not an imaging system, but a spectroscopic system. Put a bunch of little robotic optical fibers that take spectra of sources on the sky. It turns out that our optical beam is f1.2, which is really fast. And to get that into an optical fiber is hard to do, so that's not a great choice. So I think what we're likely to do is to expand the set of filters through which we take data to get more incisive spectral information, but as an imaging system. And it may well be that the long-term future of this telescope isn't in astronomy at all. If it turns out that we populate the orbit of the Earth with all kinds of satellites, some of them are going to lose control, are going to be tumbling around out of control, and you need to track them. We need like the space equivalent of the FAA and air traffic controllers. And some of those satellites are visible from radar systems from the ground, but things in geosynchronous orbit you can't see with radar. But if you were to engineer a telescope to do space traffic management, oh my goodness, it would look like this one. okay? So it may be that it just goes over into space traffic control in the aging years of its life.
Okay. Couple more questions,
Is there anything that the telescope can teach us about black holes, or that we can observe new?
Oh, there's all kinds of cool stuff. So you saw some of the video clips that were played earlier when we all came in about tidal disruption, where a black hole sort of sucks in a star and goes zoop, and all the stuff comes spewing out. That's called a tidal disruption event, and we will detect those in abundance. There are experts here at Northwestern that study those processes, and the cores of galaxies like ours contain supermassive black holes that also exhibit sort of longer timescale variability, and we can use all kinds of methods to understand the astrophysics that surround those systems. You know, by definition, we're not going to observe black holes directly. It's kind of hard to see a black hole. So that's all I would say, sort of indirect, looking at the processes that surround them.
Hello, thank you for coming. I actually wanted to ask about comet chasers. I just thought the idea of like an astronomy community science program is amazing, but I wonder if, I mean, like how the idea came about. Because I am curious if it's something that was kind of already there when folks were thinking about the Rubin telescope, or if it's something that sort of occurred to someone in the process, and how.
Yeah, so thanks for the question. There's been a long-standing tradition of citizen participation in science going back to something called Galaxy Zoo. And there was an even earlier project where people figured out how to capture CPU cycles on your personal computer while you were sleeping and use them to do numerical simulations. So I would say Comet Chasers is an instantiation of that idea using Rubin data, but I wouldn't want us for a second to take credit for that. I think there's also a vibrant public education and outreach component of the Rubin Observatory, I guess driven by our enthusiasm of making the data useful across a wide range of applications. I mean, you know, in many ways, astronomy has always been like a gateway drug for science, right? Young people get interested, it's really visual, it's really pictorial, you can get on board and participate, and then they sort of get ramped up on the whole scientific process. And so we're hugely enthusiastic about encouraging that to happen.
Okay, I know we're going to take at least 2 more. Are you okay?
I'm great.
Okay, hi. My question is about recent conversation in the news about an asteroid that is being predicted that it might impact the moon. Do you have an opinion on what we should be doing about that?
I don't know about that. I haven't read it. I think that the moon gets bombarded by stuff all the time. You've seen all those pictures of craters, right? That's how that happened. That's an interesting sort of philosophical question, right? Do we have an obligation to protect our moon? I'd have to think about that. My off-the-cuff answer is, let nature take its course. I don't think that poses any hazardous, and it's not what I would spend money on, unless it like broke the moon in half. That would be bad. I don't have a good answer.
Okay, let's take one here in the middle.
Yes, referring to the first cone you showed, where is life in there?
Right. So I would say the prevalence of life in the universe is certainly on my short list of questions that I'd like to have an answer to before I go on to something else, right? And it's certainly true that an element of that is the prevalence of planetary systems around other stars. And that's a place where astronomy has made a huge amount of progress in the last few decades, right? I mean, roughly speaking, pretty much every star has some planetary system around it, and we didn't know that was true before. How many of those planetary systems are in some habitable zone if you believe that you need liquid water to make life, which is itself debatable, is an open question. I think that There are other projects that are better suited at going after the prevalence of extrasolar planets and looking spectroscopically for evidence in the atmospheres of those planets for biological processes. One of them that I would advertise to you is the Giant Magellan Telescope, in which Northwestern just became a partner. That's a good application of the GMT and super high resolution spectroscopy. It's not well matched to this project in particular, and so that's not on the list of science goals. And I can't think of a way to observe with this telescope that would particularly be advantageous for that. Sorry.
Chris is very gracious and enjoys the Q&A, but I would like to be respectful of your...
And the audience's time. Thank you. Thank you for your interest. Thank you for coming. Have a nice evening. Yeah, go to Dearborn. They're open and waiting for you.